complex, different than the typical axial loading or just lateral loading acting on the foundation. Rather, we're dealing with different loading scenarios where you have very little axial load, but a lot of lateral load or seismic load and shaking and stuff like that. So definitely we have to be very resourceful and look at the opportunities and look at the most efficient foundation system. I'm trying to present that to you today. Okay. So that represents, Mark mentioned that I've been 28 years with Western. I've been doing research on helical piles for 28 years. So I have been doing a lot of work on helical piles, and the reason is they're a really good foundation system. So for those who didn't see helical piles before, as you see here, this is a bunch of helical piles. They are made of a central shaft, a steel pipe pile, and then fitted with 1, 2, or 3 or more helices. And the helices serve two functions. One is to put the pile into the ground, so you torque the pile into the ground like you screw a screw into the wall. And that's a very efficient installation technique. It takes 2, 4, 5, 10 minutes to put a pile in the ground, as opposed to ramming this pile into the ground for an hour, 2 hours, or sometimes a full day to get a pile into the ground. So it's a very efficient installation technique. But the second advantage is, as soon as you have this pile in the ground, these helices also help to transfer the load that you apply to the pile head and transfers to the ground in a very efficient way. Now, if you design it well, we design it such that these helices are situated in the good soil. So in any soil profile, you may have some very squishy soil, very loose material, gunk or stuff like that. You go very quickly in that soil, and then you situate your helices in the good soil, then you have a very high capacity. The good news is, even in situations like that, we develop techniques to grout around the pile. So even if the soil is just gunky, very soft stuff, we can make it even a good foundation system with this technology. So helical piles are very suitable in many ground conditions, soft, hard, but not soils with cobbles in it. So if you have large pieces of rock, you cannot install this, and definitely you can't install it in rock. But it can go in very stiff soils, and if you can't just put the pile into the soil directly, we do what we call pre-drilling, and then you install the pile in this pre-drilled hole. So it's a very efficient foundation system, goes into the ground very quickly, and offers you very efficient load transfer mechanism compared to the conventional spirit shaft pipes. And the parameters of the pipe, as you see here in this on the right graph, you see the method of installation. As I said, you torque the pile into the ground. So there is the torque head applied here. You hold the pile there, and then you turn it on, you screw it, and then this helix helps the pile to go into the ground. As I said, once it's in the ground, will help transfer the load. And you probably see marks on the pile here, and these marks are done every 1 foot, so we know how long the pile is in. But there is another advantage to that as well, because we measure the torque applied to the pile head, and then eventually you can correlate the measured torque to the pile capacity. And this is a huge advantage for helical piles, because that works as a quality control measure. If you achieve a certain torque, you know that you achieved a certain capacity for the pile even without testing. So we actually sometimes we design helical piles based on the measured torque. And in the design document, you state that you have to achieve a certain torque applied during the installation. If you don't achieve it, that means you then achieve the required capacity. So you continue to go deeper until you achieve the required torque. So it's a very good way to ascertain the capacity of the pile right on the spot. You don't have to have a very expensive, cumbersome pile load test to ascertain the capacity of the pile. So this is another big advantage for helical piles. This image shows the different design parameters for helical piles. So we have the shaft. So like I said, this is like the conventional shaft of a steel-driven pile. So it offers you the same capacity. But on top of that, we have the helices. And these helices also help to transfer the load applied at the pile head to the soil. And the good design with require these helices placed in the good soil within your profile so you can actually generate significant bearing resistance. Then the total pile capacity for a helical pile will be made of the load transferred through the shearing resistance along the shaft and the bearing resistance along each of the helices. But we also found that if we vary the spacing between the helices, we can reach a situation where we generate a soil cylinder between the two helices where you have significant shearing resistance along that. But we needed to understand this. We've done a lot of testing and a lot of numerical modeling to understand the load transfer mechanism, and then we use that to develop a design methodology based on the experimental data from full-scale field testing and from advanced numerical modeling, as I'm going to share with you. So the motivation for today's presentation and for the 28 years that I invested in my life to work in helical piles, we've seen significant increase in the use of helical piles. When I started to work on helical piles in '95, no one actually knew about helical piles. It's a known foundation system, like 100 years old, but it wasn't used. In Canada, it was only used to support light poles. So you would find the helical piles used to support light poles, sheds in the backyard and stuff like that, very lightly loaded structures. When I mention helical piles to engineers, no, we will never consider that. And then I continued to do research on that, and I continued to work with companies to improve the installation technique, the equipment required to install the piles, and then that allowed us to increase the size of the piles. Initially, the first piles I've done testing on was only 2-inch in size. Now we have these, so I'll show you some of the testing here, where the piles were 10-inch, 11-inch, and I've done piles even larger than that. I had a major project in New York last year. So the power transmission line, the high voltage power transmission lines for the state of New York were actually supported by helical piles. Very large diameter, very large capacity, and very large depth because it was really gunky soil in that area. So that's one of the motivation there, that we have seen significant increase in the interest of helical piles because of all the advantages they offer to us. Also, we have significant advancement in installation equipment. So the main piece of equipment is the drive head that is connected to any construction equipment that you have, and then you can use it to torque the pile in the ground. When we've done the initial work, I have here Dr. Yasser Abdelghani. He's done his PhD under me. He actually worked on helical piles, and the largest drive head at his time was only 10,000 pound-foot. Guess what we have right now? I used a machine that has 400,000 pound-foot, 40 times more powerful than this guy, right? So that can install a lot of piles into the ground, and that's not the largest machine in the world, by the way. This is the largest machine I was able to convince a company in Canada to manufacture and use. But now they use helical piles to install wind turbines in the ocean. So they use a much larger helical pile, Chinese companies, much larger helical piles with much larger helices that can generate very significant capacity. We also have seen the helical piles, like I mentioned. I do a lot of work on foundations subjected to dynamic load, seismic loading. So we've seen helical piles installed in applications where they are subjected to dynamic loads. No one knew how helical piles will respond to a dynamic load. No one knew how a helical pile will respond to seismic loading. So we really needed to understand the load transfer mechanism under dynamic loading or under seismic loading conditions, and we had to do this kind of research. So we've done a lot of studies, many PhD students, many master students, spent many of their good years learning how to characterize the axial and lateral performance of large diameter helical piles. No longer 2-inch piles. Now we're talking about a much larger helical pile. We looked at the effect of the soil disturbance because that was one of the reasons many engineers didn't want to consider helical piles. They would say, as you turn the helical pile into the ground, you disturb the soil. You shear the soil, so you weaken it. No, I don't want that. So we wanted to evaluate and characterize the soil disturbance. And if it's truly happening, then we look at a way to mitigate that, and we looked at that, and we developed the techniques for that. Then we looked at the dynamic and seismic performance of helical piles. Like I said, it's a very efficient foundation system, very quickly put in the ground, especially if you work on a site where you already have equipment. So let's say you have a power plant, and then you want to add another unit to this power plant to expand the capacity. You cannot bring in a pile driver into a working site where you have large compressor or turbo generator is operating. But you can bring a small machine with a drive head connected to it, and you can install helical piles. And that's why this has become a very popular foundation system. Definitely in Alberta, that's the oil and gas land. And all the projects now in Alberta, they actually look at helical piles first. If it can't work with a helical pile, they consider something else. As opposed to in other places where the helical piles is a big convincing matter. The one project that I did here in this city, actually, we used helical piles to support hotel development. And is there anyone here from Pacific? Yeah, so we did that with Pacific at the time. They were opposing to using helical piles, but I said, well, let's put piles in the ground and test it and see what the capacity is good. And after we've done the piles in the ground and tested it, they loved it, and then that was the foundation system we used to support the piles. So anyways, over the years, we've done a lot of research at Western to look at the load transfer mechanism for the helical piles under axial and lateral loading, monotonic and cyclic loading, dynamic and seismic loading. We looked at the capacity in installation torque correlation. As I said, that's one of the main advantages of helical piles. If I measure the torque applied to the pile head to install it in the ground, I can correlate that to the capacity of the pile. So right on the spot, I can tell you that this pile can achieve whatever capacity it is designed for. We looked at the helical pile configurations. We looked at helical piles with small shaft, large diameter shaft, with one helix, multiple helices, with a tapered shaft. So we looked at different ways of constructing helical piles. We looked at the effects of the pile installation on the disturbance of soil, and that can affect the capacity. So we came up with a method to calculate the capacity of a helical pile in a ground that is susceptible to disturbance due to the installation. And we also looked at the different loading schemes, as I said, static, cyclic, seismic, dynamic, and all of it. So today, I'm going to kind of give you a very summary, very quick run-off of all of that. So the first thing is the load transfer mechanism, because it's very important to come up with a way to design these piles. So what we found that for helical piles, when you apply the axial loading to the pile head, it transfers to the soil through one of two mechanisms. The first mechanism, this one, where some of the load is taken by the shaft through shearing resistance along the shaft, and some of the load is taken by the bearing resistance along the helices, as well as the pile toe if the pile toe is closed. So the capacity of this pile in essence is equal to the capacity of the shaft plus whatever additional capacity you can generate from the helices. And the good design will imply, as I mentioned before, that these helices will be designed to be sitting within the good soil layers. It offers you maximum capacity for the optimized cost of the pile. The second load transfer mechanism, when you have the helices close enough to each other, then you would have shearing resistance along the shaft of the pile, but also you have a cylindrical soil zone between the helices, and then you have shearing resistance along the cylindrical soil. Then we call this individual bearing plate system, and we call this cylindrical shear system, or failure mechanism and failure mechanism. And we needed to assess what are the parameters that cause the load transfer mechanism to follow this individual bearing, and what is the mechanism for the geometrical design that leads to the cylindrical shear failure mechanism. So to do that, we've done a very systematic, consistent, comprehensive studies where we gathered very high quality test data from full-scale tests. So we've done several tests in the field, different piles installed in different ground conditions, and we applied the load to them, and we instrumented the piles to measure the load distribution along the pile. So we know how the load was transferred, applied at the pile head, and then transferred to the soil at different elevations. So we were able to evaluate that. And then we got this data and used it to calibrate and validate numerical models, finite element models, and then we used these calibrated finite element models to perform very comprehensive parametric studies considering different types of soils, different configurations for the piles, and to understand the load transfer mechanism, what causes it to behave this way or that way, and then we use that to establish design methodologies, and I'm hoping you will see them in the next version of the Canadian Foundation Engineering Manual, which is actually almost released now. So you will see the design approach for helical piles in that. Then you can actually design the piles and make reference to the Canadian Foundation Engineering Manual. This is one example for the pile load test that we've done. This testing was done in Alberta, so we installed in this a number of piles. Some of them was a single helix, some of them it was 2 helices. We varied the spacing between the helices, trying to understand what causes individual bearing versus cylindrical shear. We had some piles that are 6 meters long, some piles that are 9 meters long, and to make this study comparative, to see the efficiency of helical piles, we also installed driven piles with the same configuration as helical piles. So the same shaft diameter, same wall thickness, same length as the helical piles, and we subjected all of them to the same type of loading at the same time frame. So if we tested after 2 weeks, we tested after 2 weeks for both helical piles and driven piles. And then we waited 9 months, and then we tested helical piles and driven piles to compare apple to apple and see what the effect of the disturbance of the soil on the capacity of helical piles and also on the capacity of driven piles. Because the disturbance of soil also happens due to the installation of driven piles. But not many people know that. So we wanted to assess the two in this comparative study. And then for all of the piles, we actually instrumented the piles. We understood the load distribution. So these are the configurations of the piles. When you see here, SS1, that's a short single helix pile. This is short double helix pile, but the spacing is 1 diameter between the 2 helices. And then SD2, so short double helix with the spacing 2 times the helix diameter and so on. And then L, that means a long single helix pile, long double helix pile, 1, 2, 3 spacing. This is the reaction pile, and this is a driven short pile, driven long pile. And as I said, the piles were very similar between helical piles and driven piles, with the only difference being the helices and the size, the number of helices. And we've done the testing, as I mentioned. We instrumented the piles and we took measurements to allow us to get the load settlement curve for all piles, and we used that to determine the capacity using appropriate capacity or failure criteria for helical piles, because we didn't have one. Remember that we have the failure criteria for the straight shaft piles. Let's say Terzaghi says the ultimate capacity of the pile is the load that causes settlement equal to 5% of the pile diameter. But was this going to work for helical piles or not? We didn't know. So we had to establish a failure criteria for helical piles. So that's another one of these study items that we've done. But what I want to highlight for you today, a comparison which shows the efficiency of the helical pile system. So if I look at this one, this is the short single helix pile, gives a capacity of 844 kilonewton, and that's 844 kilonewton. It's not a small pile, that's a large capacity pile. And I compared that with the same length driven pile, and give me here 720. So this is 20% higher than this one by 1 helix that we just added. And even that helix was not placed in the strongest soil layer in this profile. When we added the second helix, and that's second helix was situated in the good soil. Now the capacity here is 1300 kilonewton, while the capacity of the driven pile that has the same length is 840. So this is more than 50% increase in the capacity of the pile due to the addition of this second helix. Now, even better than this, if I look at the long double helix pile and I compare it with the long driven pile, look at the difference in capacity here. Significant increase in the capacity, almost 300% increase. And the main advantage that we happened here that led to this very significant increase in capacity, that we allowed sufficient time for the soil to regain strength, and the capacity of the pile was higher. Because this pile was tested 9 months after installation. So yes, helical piles may disturb the soil, but driven piles will also disturb the soil. If we allow enough time, the soil will regain strength, and then you have very significant higher capacity from helical piles compared to driven piles, and increased capacity for a double helix pile compared to a single helix pile. And as I mentioned, all piles were instrumented with strain gauges, so we're able to determine the load transfer mechanism, how the load is transferred to the different soil layers, and we use that to establish the load transfer mechanism. Is it individual bearing plates or the cylindrical shear for the different piles tested, considering the different soil profiles we've done. And then, as I mentioned before, I got this data, used it to calibrate and validate numerical models, and then I used the numerical models to do significant parametric study to look at different soil conditions, different spacing between the helices, different ratio for the helical plate diameter compared to the pile shaft diameter, and so on. And based on that, we developed an understanding of what causes the load to transfer in that individual bearing mechanism and what causes the cylindrical shear mechanism to happen. And then, based on that, we developed the design methodology that you can use. But just because we used finite element models, so we wanted to make sure that these finite element models can actually predict the performance correctly. So you see here a comparison between the predictions of the finite element model with the measured responses, and as you see, good ability of the numerical models to do that. Then we conducted, as I mentioned, a parametric study where I varied everything in the design for the helical piles and used the numerical models to establish the performance of not just the piles, but also the soil around them, to also understand if you have a number of helical piles within the group, if they are going to interact. Is this going to reduce the capacity? Is this going to increase the settlement? Because these are other design requirements. You want to make sure that you have the piles in a group, they are not going to experience reduction in the capacity because of the interaction between the piles, and you want to make sure that there is no extra settlement because of the interaction between the piles. So from the finite element model, we established the zone of influence for each of the piles and for each of the helices. So establish, you see here, individual bearing. There is no overlapping of the stresses, so that behaves in the individual bearing mechanism. But here you have overlapping, then that will behave as a cylindrical shear. And also we found that the maximum extent for the soil vector, for the movement of the soil, is about 40% of the helix diameter. So if I place the helical piles at a spacing equal to a minimum 2.8 times the helix diameter, there is no interaction between the piles, then in this case you can actually calculate the capacity of a helical pile group as the sum of the individual capacities of the piles within the group. No reduction in the capacity of the piles. And accordingly, we developed a design methodology for helical piles in sand. So you can use this equation, and everything we have here is an engineering standard geotechnical parameter. Nothing less than what you actually do in the conventional driven piles or cast-in-place concrete piles. So these equations are based on everything that we learned in school for the design of piles, but with the consideration of helical piles having different helices. So we look at the area of the different helix and the bearing acting on each of the helices and so on. And that's for piles in sand, and similar equations for piles in clay. And all of that work is actually published in reputable journals. This in particular is published in the Canadian Geotechnical Journal. And as I said, you will see these equations in the next version of the Canadian Foundation Engineering Manual. We talked about the issue of the soil disturbance and how it affects the capacity of the pipe. So we actually evaluated that based on measurements in the field, and we developed a methodology to account for the effect of the disturbance. So the soil shear strength will decrease, then the capacity of the pipe will decrease. So we'll provide you a methodology to account for that for the case of the cylindrical shear failure or the individual bearing failure. We have a proposal for that, and we actually validated this design methodology against many tests for piles installed in what we call structured soil. So you know structured clay, when you disturb the clay, it loses a lot of its strength. So we accounted for that, and we demonstrated that this methodology provides you reliable assessment of the capacity of the pile in structured soil. The other issue that kind of prevented many engineers to consider helical piles initially is the issue of the settlement of the pile foundation. In many geotechnical reports, because I do a lot of consulting, I read the report, and the geotechnical engineer would state in the report, yes, you can use helical piles here, but they put a warning note that the settlement of these piles is large. So you have to make sure that you don't exceed settlements. So I wanted to know why they are making these statements. I haven't seen settlement of helical piles to be greater than other piles if you design it correctly. So I've done part of my analysis to look at the group effect and the increase in the settlement of a pile group of helical piles, and I found it to be no different than the increase in settlement of a helical, of a pile group based on the spacing between the piles. So I developed a similar chart like this one is for helical piles, which shows the increase in settlement for the piles within the group compared to the settlement of a single pile, and it's exactly the same as driven piles. So there is no reason to believe that helical piles will settle more than the driven piles. As a matter of fact, I will demonstrate to you later, in seismic applications, the helical piles will settle much less than the conventional straight shaft piles. So there is no reason to say helical piles will settle more than other piles. As a matter of fact, it will settle much less than other piles if you design them correctly. The other issue related to the comparison between the performance and evaluation and design and assessment of helical piles compared to cast-in-place concrete piles or driven piles is how to measure the capacity of the piles. As we all know, the standard static load test is the accepted method. It's an ASTM standard test. We are all very familiar with it. If you have a very large capacity pile like helical piles we demonstrated, then perhaps you need to do something like this, which would take forever to set the test and get the results, would be very expensive. So instead, we go for reaction systems like these. And one of the tests that I have done, look at this one. So one pile, we actually had to do 2 reaction beams, and you have to have very large loading jacks. So the cost of the setup is very significant. So instead of doing that, we opt sometimes for using the PDA, the Pile Dynamic Analyzer. So it is very widely used for the conventional piles, typically for driven piles, standard testing technique for driven piles. But we also use it for precast, cast-in-place concrete piles or precast concrete piles. But we didn't really know how to use it for helical piles, because one of the main requirements for the high strain dynamic testing, or the impact loading of the pile head, and to measure the movement of the pile under that effect, is you need to satisfy 2 things for a successful design of the test. The first one, that you don't damage the pile. So if you impact the pile too much, you will damage the pile head, then you lose this pile. The second requirement that you need to mobilize the pile sufficiently so you can actually determine the capacity. So if you impact it very hard, you damage it. If you impact it very soft, you don't mobilize the capacity. You don't measure the actual capacity of the pile. So there is a sweet spot between the two. If I know what the impact energy will cause in terms of a peak force acting on the pile head. And that was the key missing ingredient for applying the high strain dynamic test to helical piles. How do we determine the peak force that will be delivered to the pile head in a high strain dynamic test? So to get to that, we really needed to understand how it is done for the straight shaft pile. So in the straight shaft pile, the high strain dynamic testing involves placing accelerometers at the pile head, and then you impact the pile, and we know the weight of the mass falling on the pile head, and we know the falling distance, so we actually know the potential energy that is delivered to the pile, and we use that to get the movement of the pile. And then there is the method implemented in the software that runs this pile dynamic driving analyzer, and that software uses a very important parameter for the design of the test, and this parameter is known as the pile impedance. So the pile impedance relates the applied load to the pile head to the characteristics of the impact loading, so the weight of the mass, the distance, and so on. And as I mentioned before, the two conditions for a successful high strain dynamic test that you actually need to mobilize the pile sufficiently to derive the capacity. So this test was not successful because you apply the load, the pile sends a bit, and then moves up again, so you didn't really mobilize the pile. But this one was successful because now I moved the pile sufficiently to mobilize the total capacity of the pile. Here, these tests were not successful. So that was the main issue for applying the high strain dynamic testing to helical piles. We don't know how to mobilize the pile. We didn't know what force should be used or how it could be used. So in terms of the weight of the mass, the falling distance, the caution applied to the pile head. So we needed to come up with an approach for that. The approach that was developed for the conventional piles considers the weight of the hammer that falls on the pile. It considers the falling distance. It considers the design of the cushion. But most importantly, it considers the dynamic behavior of the pile and the surrounding soil in terms of what we call the pile impedance. And that was the main thing that we were missing for helical piles. We know the impedance for straight shaft piles, but we didn't know the impedance for a helical pile. So what we did, we looked at the equation. So we looked at the derivation of the equation for the impedance for the straight shaft pile. So the impedance for the straight shaft is Z. We didn't have a similar value for helical piles because we didn't know what's going to happen when you impact the pile head. So we actually considered working with several companies doing the high strain dynamic testing to many piles, helical piles, in different types of soils, and we collected the data, we evaluated the data, and then we started to develop an analytical model that actually accounts for the behavior of a helical pile based on these data. What we found that this is the curve that represents the peak force. This is the peak force versus the impedance for pile, and we found that this curve fits very well the data for driven piles, but it didn't fit the data for helical piles. And that's just an example here to show you how different the two piles respond to the impact loading. So we wanted to evaluate that in terms of an analytical model. So we ended up, after we've done the finite element analysis considering the impact load in the helical piles, we understood how the soil moves with the helical pile, and we found that a soil cone underneath the helix moves with the pile when you impact it. So we considered this soil mass and the damping of the soil as you impact the pile, and based on that dynamic model, we developed an an equation for the impedance of the pile. And we use that to evaluate the peak force that will develop at the pile head. And similarly, for a helical pile with two helices, we developed a similar model. So you have the cylindrical soil zone between the helices, as well as this conical soil mass underneath the pile toe. And we use that to establish an impedance function for a helical pile with multiple helices, 2 or 3 helices. You look at the interhelical cylinder zone, and you look at the conical area of the soil underneath the pile top. And based on that, we were able to establish the good estimate and good predictor of the force. And as you see here, we're able to come in a range where actually there is a correlation between the impact force and the different parameters of the test. So we're able to predict the peak force. Then we're able to design a high strain dynamic test for helical piles, and we use that to get the capacity of the pile. Another issue that actually is an advantage for helical piles is the response for the pile to lateral loading. To start, a helical pile has a straight shaft similar to the straight shaft like I showed you the picture. You have the shaft of the pile, and then you have several helices connected to it. So there is no reason to believe that the helical pile will give you a lateral resistance less than a cast-in-place concrete pile or a driven steel pile, because it's just based, when you apply the load to the pile head in the lateral direction, is based on the flexural rigidity of the pile. And it's the same for the helical pile as a driven pile. I would say actually the helical pile has an advantage if you design it right. If you place the helices at the right location where it can actually contribute to the lateral resistance. And to achieve that, again, we quantified the performance of helical piles under lateral loading. So we've done full-scale load tests, we've developed analytical techniques, we've done numerical analysis. So all of that was done to understand the load transfer mechanism of helical piles under lateral loading. And here is what we found. If you place the helix well below the ground surface, well below where you apply the lateral load, then the helical pile will behave exactly the same way as the conventional straight shaft pile, because the lateral resistance is based on the flexural rigidity of the shaft. But if you place at least one of the helices closer to the ground surface, so when you start to apply a lateral load to the pile head, as you have this lateral deflection, you also have bearing resistance on the helix, which will increase the lateral resistance to the lateral load, and also will reduce the lateral deflection. So it will improve the performance of helical piles under lateral loading compared to straight shaft pile. And we demonstrated that, as I said, through different pile load tests in different ground conditions, different length of piles. And we found as we increase the pile length, the additional advantage for the helical pile is diluted. We don't have as much contribution from the helices. But at the end of the day, we found that the effect of the disturbance, again, we've done testing after 2 weeks and after 9 months, and you see an increase in the capacity as time lapses, and you have the soil regain. This is one of the main criticism for helical piles. If you allow enough time, the soil regains strength, and then it gives you the capacity. Another aspect that relates to helical piles, engineers said, well, we know I can use L-pile to calculate the lateral performance of straight shaft piles. How can I do it for helical piles? We actually demonstrated you can use the same technique. We use the same tool, L-pile, that many of us use for calculating the lateral performance of piles. You can use it for helical piles, and we demonstrated that. We used the L-pile or the PY curve approach, determined the performance of the piles, compared it with what we measured, and we found very good agreement between the calculated and observed response. But what we also found that most of the deflection for helical piles or straight shaft piles occur in the top 10 pile diameters. So if I want to take advantage of the helical piles, then you have to place at least one helix above that level. So you can't have all helices below 10 times the pile shaft diameter. So if the pile shaft diameter is 300 millimeter, then you have to have at least one helix above or closer to the ground surface within 3 meters to have an advantage for you. And as I said, we demonstrated that the L pile and the PY curve approach can be used for helical piles. And as a matter of fact, we developed PY curves specific for helical piles installed in structured soil because the installation will disturb the soil, so it would affect the value of the PY curve. And we demonstrated how it works, and we demonstrated that it gives really good results. Now, these are two exciting things that have come recently. First, we developed this technology. Yasser was part of a patent that we developed something like this. And Chance, the company Chance that produces helical piles, took this patent. Unfortunately, like, you know, when Microsoft buys a software just to kill it, that's what they did, actually. I was very disappointed at what they did. So they buy the patent to kill it because they want to promote another technology they have. So that's what they did. But anyways, working with this company, it's called Magnum, we did this project in New York. We used very similar technology. So we grouted piles as we installed them in the ground. And as I mentioned, we used this to support the high voltage power transmission lines in the state of New York. And the way this works, as you install the pile, you have a setup there, so you can actually apply the grout. And as the pile goes down, the grout forms a grout column around the pile shaft. And that serves two functions. The first function, that you increase the diameter of the pile shaft, which increases both the lateral and axial capacity of the pile. But the second very important feature for this, if I have soft soil here or a soil that is disturbed due to the installation of the pile, the grout mixes with the soil and then it mitigates the effect of the soil disturbance. Another feature that in some places could be very important, if this soil is corrosive, then the grout column here applies as a protection from corrosion for the pile. So that's another added advantage. And as I mentioned before we did this project for the state of New York, we installed piles, we tested them, we demonstrated that they provide the capacity and performance requirement for the high voltage power lines. Just as an example here, this is the load displacement curve for the grouted pile. This is the load displacement curve for ungrouted piles. You see significant improvement in the performance of the pile due to the grouting technology. Then the second development that I really liked about helical piles, as I said, we started to use it in applications where the piles are subjected to dynamic loads, either seismic loads or shaking due to dynamic loading from equipment. So we subjected the piles to these types of loading. So we've done here that is dynamic loading at the pile head, similar to, now it's not gonna run. I told you it's not gonna run. Okay, so that was supposed to vibrate actually. No, it has to be there.
Give it a shot here.
Yes, here it is. So this actually, thank you. So as you see here, we are applying, the video is moving, but this is a shaking machine that causes harmonic loading on the pile, and we measured the response of the pile, and we varied the frequency of the load, and we looked at the variation of the stiffness of the pile as the frequency of the load changes. And we also did lateral load testing, cyclic loading. One of the things that we measured also the torque applied at the pile head, and as you see the consistency of the measured torque, and as I said, that can be used as a means to ascertain the capacity of the piles. So this is lateral load testing using these jacks. One thing that we noticed, and I'm going to emphasize this after testing, that when you start to shake the pile back and forth, you actually create a gap between the pile and the surrounding soil. And this gap affects the stiffness and the capacity of the pile big time. And if you don't account for it in your design, you cannot predict the performance of the pile or the capacity of the pile under lateral loading. And this, by the way, applies to helical piles, and applies to cast-in-place concrete piles, and applies to driven piles. And unfortunately, many engineers do not pay attention to this. So the detail on the cap, if you are doing performance-based design for, let's say, extended shafts, I don't know if you use them. Actually, you do use the extended shafts here. So you have the cast-in-place, large diameter reinforced concrete piles to support bridges. When you do the performance-based design for these things, you have to account when this extended shaft, which is a pile that extends and operates as a pier for the bridge, when it starts to shake during the seismic event, you create a gap between the pile and the soil, and that gap affects the performance of this pile. So anyways, we found that when we try to analyze the response using the characteristics of the pile and the soil without accounting for the gap, we couldn't get the performance. Here's what we get using the L pile if I don't account for the gap, or I don't account for the disturbance that happens in the soil due to the loading, so degradation in the strength and stiffness of soil. So we try to account for this degradation, we get the second curve, but it's still not matching the observed behavior, not until we actually looked at the gap and we modeled the gap, and as you get with the gap, you find yourself much closer to the measured response. So this is the estimated response considering what we call increased projection, because now we have a gap opening between the pile and soil. It's like the pile is projecting above the ground, and that increases the lateral movement under the lateral load. And we've done also full scale dynamic loading for the piles in clay and in sand. So very quickly here, and the one thing that I wanted to draw to your attention, the behavior of helical piles here showing some peak response resonance condition. That's exactly the same as the straight shaft pile. So there is no difference between the two. But the most important feature that we learned from this testing, that as you increase the load, you increase the nonlinearity, then the natural frequency shifts. And then you have to account for that in your analysis. So you can run the analysis using a linear approach or a nonlinear approach. Linear approach, you don't account for the degradation and the strength or stiffness of the soil. Then you can't actually predict the dynamic behavior of the piles. But if you do the nonlinear analysis, you can predict that. So to demonstrate this very clearly, this is the measured response, which is nonlinear in a way. And that is the calculated response if I assume that the soil has no degradation and there is no separation between the pile and soil. And you see the natural frequency of the pile is here, but the calculated natural frequency is here. You are way off. And if I use that in the design, then it's a disaster, because I do this all the time. If you cannot predict the natural frequency of your foundation system, you are going to make a huge mistake in your design. So what we did, we looked at nonlinear approach. In the nonlinear approach, we considered the nonlinearity of the soil around the pile, and we also considered the gap opening between the pile and soil. And when we consider these two things, look at the comparison between the measured and calculated responses. Perfect match now. So you have to account for the nonlinearity, and you have to account for the gap opening. When you do seismic design, this is a must. If we don't account for that, then the natural frequency of the foundation system you are calculating is no match of the actual behavior under an earthquake loading condition. And we also found that the load transfer under dynamic loading is mostly taken by the shaft, both under axial loading and lateral loading. Hence, The helical pile behaves exactly the same way as the conventional straight shaft pile. So there is no reason to say helical pile will not work under dynamic loading. It will work under dynamic loading, and you can actually use the same tool. In this case, we use the program Dyna 6, which is very widely used, and it's actually marketed by Western, developed at Western. That's used worldwide for the design of foundations subjected to dynamic loads. And here is the distribution of the load, the dynamic horizontal load, and as you see here, the horizontal load in this case was up to 3 meters from the ground surface. The diameter of this pile was 324 millimeters. So the dynamic load is taken by the top 10 pile diameters. Not much transferred below that. So if you want to benefit from helical piles, you have to place the helices at this elevation. The last one, and I promise you this one, but it is the most exciting one for you here in British Columbia. The seismic behavior of helical piles. So I have done, again, full-scale testing of helical piles under full-scale earthquake load. Can you imagine that? So we're able to install piles, full-scale, and then subject them to full-scale seismic loading. And before we get to that, I wanted to give you the motivation for me to consider this. During the Christchurch earthquake in New Zealand in 2011, they found that many buildings that were supported on conventional straight shaft piles experienced significant differential settlement, as you see. This building experiences 29 centimeter settlement on one side, 4 centimeter on the other side. So 25 centimeter, 250 millimeter differential settlement between the two sides of the building. And the building didn't collapse, but this building ended up being useless after the earthquake because many cracks in beams and columns and the architectural walls. But worse than that, all doors and windows are no longer operating because of the differential settlement. So basically, you have to demolish this building to put a new one because of the differential settlement. Many of us consider liquefaction as a cause of failure for the building. But most importantly, liquefaction of soils can lead to significant differential settlement, and then this differential settlement will render this building of no use, right? So this is a very important consideration to control not just the capacity, but also the settlement and the differential settlement of a building during and after an earthquake. The other picture there, this is another house that has actually experienced significant settlement, as you see here, again because of liquefaction of the underlying supporting soil. On the other hand, these two pictures from Alaska, after the big earthquakes that happened in Alaska, and as you see, the houses are beautiful, the barbecue is still there, right? No damage. Why? Because these houses were actually supported on helical piles. So we wanted to know why helical piles perform so well under earthquake loading. So we've done the studies. Well, as I said, we characterized axial and lateral performance, but we didn't really understand the seismic loading. So what we did, we conducted a study using the large high performance outdoor shake table. It's one of the largest in the world. You see the steel box back there. This is a very large steel box that we use to enclose soil. So in this case, we enclose sand inside it, and it sits on the shake table. We install the piles in the sand inside the box, and then the shake table shook the whole thing using earthquake signals. So what we did, we installed 10 different piles with different geometries. So first, we tested the soil in the soil box with no piles. And then we installed the piles and we tested the piles with no loads acting on them. And then we added loads. As you see, these are large concrete blocks that represent the actual weight that will be acting on a pile head if it is subjected during an earthquake, supporting a house or a building. And then we connected 4 piles and 4 piles with a very large load to mimic the weight of a house. So we considered the behavior of the soil alone, the piles alone, the piles with load, and then piles in a group, and we compared the response. So this project actually allowed us to understand the performance mechanism of helical piles during earthquakes. And it was very well instrumented, many accelerometers within the soil and on the piles and on the masses acting on the pile heads. And as I mentioned, we have done testing the first day in the soil bed alone, second day on the piles in the soil bed but no loads, and then the third day we have loads on the individual piles, and then the fourth and fifth days we had loads on groups of piles. And I have description of all of this, and if you are interested I can share with you the publications that came out of this work. Here are the configuration of the different tests we conducted, and I will share with you some of the results that relate to the different types of testing. We've done small PGA testing to get the dynamic characteristics, and then we've done very significant earthquakes. These 2 earthquakes are very strong earthquakes. The one that happened in Northridge in California in '94, and the one that happened in Kobe, Japan in 1995. These are very strong, but they have different frequency content. So one has a wide range of frequency and one have narrow range of frequency. So we wanted to evaluate the effect of the frequency content on the pile performance as well. So we've done all of this, and I'm going to share with you just a very small sample of the results. So this is the shaking test for the individual piles. You see how much movement for the soil box here, and concrete masses on top of each of the piles is actually the actual weight this pile would be designed to support. Nothing happened to the pile, but look at what happened between the pile and soil. So this is the gap that opens there that I mentioned, and that affects the performance of the pile, and you have to account for it in your design. And this is the pile group test. Again, very significant shaking. You see, this is the shake table, the yellow thing down there, significant movement. But then again, you see the gap opening between the pile and soil. And we analyzed the experimental data. As I said, we had accelerometers within the soil and on the piles. We were able to establish the performance of the piles from the experimental data. We were able to analyze the response using the program Dyna6. But most importantly, and that's the key thing for understanding how helical piles work. If we look at here, let's say for this graph, when we have linear increase in the intensity, we found that the single pile sees very significant increase in the deflection. Because under lateral loading, the resistance of a single pile is a function of flexural rigidity. And as you increase the lateral load, the gap opens more, then the flexural rigidity of the pile soil system decreases a lot, and you have sharp increase in the deflection of the pile. So this is for single piles. But when we look at the pile group, look at what happens. As the intensity of the earthquake shaking increased, we did not see an increase in the deflection of the piles. As a matter of fact, we've seen a decrease in the deflection of the piles, relative decrease. So that is a very interesting observation. Single piles experienced large increase in the deflection, but the piles within the group did not see an increase. To the contrary, we've seen a reduction in the response. So that told us something. There is a difference between the performance of the single piles and the performance of the piles within the group. And that difference was very significant between helical piles and the conventional piles. We found also that the bending moment for the piles within the group, so this is the pile group, you'll see the bending moment here is much less compared to the bending of the single piles. So the piles within the group performed much better in terms of reduced displacement, but also reduced bending moment. That means this group can take a much larger earthquake loading compared to single piles. So what caused this to happen? And we actually were able to figure what happens. And here is a direct comparison between the performance of the single piles and the pile group. So this is the normalized response of a pile within the group, and that's the response of the individual piles. And you see big difference between the two. And the reason for this, we found that the load of a pile group is carried primarily due to the rocking behavior. And the rocking behavior of the group is a function of what? The axial resistance. And the axial resistance of helical piles is superior because of the additional capacity from the helices. So even if the helical plate is not placed near the ground surface, it will still contribute significantly to the seismic performance of the foundation if it is part of the group. When it is part of the group, as I said, the behavior is no longer based on flexure, it is actually based on rocking. We found that 80% of the response is related to the rocking behavior of the pile group, and that made the response of the pile group much more efficient than single piles and more efficient than conventional piles. And then this is our last thing. We've done numerical modeling. We understood the behavior. So we needed to understand, if I add more helices, is this going to improve the behavior? And we actually found that these additional helices add significantly to the axial resistance, which actually improved the seismic performance even further, even though that the helices are not at the ground surface. They are not close to the ground surface. But just by virtue of increasing the lateral the axial resistance, it improved the lateral resistance. The last observation that is very important, this is the settlement of a driven pile. So D is the settlement of the driven pile. This is the settlement of the helical pile. Look at the difference between the two. And that's what made the performance of the building supported by helical piles much more superior, much safer than the performance of the buildings that were supported on driven piles. I have another testing here, similar, but for now liquefiable soil. So the previous one for dry sand, this one was testing in the lab. This is the lateral displacement of a precast reinforced concrete pile. This is the performance of two piles, one single pile and one double helix pile, one single helix and double helix pile. You see the difference in response. When the soil liquefies, the reinforced concrete pile had no resistance. But for the piles with helices in dense sand layer at the bottom, sustain the lateral load and reduce the lateral displacement so much. But similarly, what we found for the single helix and double helix pile performed much better than the reinforced concrete piles. So significant improvement in the performance of helical piles compared to cast in place concrete piles due to the significant increase of the axial forces. As you see here, these are the measured axial forces during the earthquake. This is the axial force due to the static loading. So you see a significant increase. That increase due to this rocking behavior, and that is the main mechanism for supporting the loading during a seismic event. So to conclude, helical piles perform awesome under axial loading, lateral loading, cyclic loading, seismic loading, dynamic loading. I hope you would consider it. And I'm promoting that. I have to declare, I don't own any helical piles company. I have no shares in any company that does helical piles. I have no direct financial benefit from using helical piles. I just do it because I know this is the right thing for us as engineers to provide the most sustainable design for projects. We were discussing in our way the changes in the climatic event and the climate change impact on the environment and how it is impacting our lives. One way to address this is to do sustainable designs. And that is one sustainable design for foundations. Thank you so much for your patience. And